very close to Crossroads. So we'll probably send out, if I know how many, and if everyone in this room loves surveys, right? We'll probably send out a survey of some options and then see which one makes the best time.
I'm not real knowledgeable about Neptune, but there are people in the club. I know you're good at it.
We got a few.
So I'm serious. When is this? Which Saturday are you talking about?
I'm gonna kind of poll the general interest to see which days work best.
Yeah, it's great weather
Saturday,
for it.
A Sunday, whatever date we can get the most amount of people to attend is what we'll end up doing. So, and again, it'll be
All right, very good. I like doing things from my smartphone here. Okay, so our speaker tonight is NASA Solar System Ambassador Tony Rice, and his talk tonight will be on planetary atmosphere. So Mr. Rice is a software engineer out of Research Triangle Park. As a solar system ambassador, he speaks at area museums, libraries, and schools. This museum in particular. Okay. And you do a lot of stuff with the planetarium, I assume. Quite a bit, yeah. Yeah, quite a bit with Moorhead Planetarium, Chapel Hill. And he is a frequent guest on the local television news station here in Raleigh, WRAL, in which he discusses current NASA missions and how astronomical phenomena are relevant to current local weather forecasting conditions. One thing I'll add in there that I thought was kind of cool that she had said this past winter when we had that big-time cold snap, that she said that the highs on the equator of Mars that whole week were higher than it was here in North Carolina. Yeah. So, I don't know, climate change, call it whatever you want, but yeah.
Let's not go there.
Yeah, my fault. Anyway. Okay, and also I want to personally thank Tony because you may remember like 2 weeks ago we had a little get-together well, not a little get-together. The American Meteorological Society came to Raleigh over at the, what was the name of that place? Yeah, thank you. Raleigh Convention Center. And where we were going to originally set up our telescopes, it didn't work out so well, so we had to move away from that location. But Tony saved the day and made sure that everybody who was there came down and saw us on the side of the building where we were able to see good views of the sun at sunset. And then after that, we looked at Jupiter and Venus, and at the end of the night, we actually looked at Saturn. I looked at a globular cluster. Only one person was able to make it out. But we still got a lot of wow factors, and that's all that mattered. So thank you. So anyway, without any further ado, take it away.
Thank you very much. And I actually wanted to start out with that. Who was out for the AMS meeting? Who brought scopes out and helped out? Thank you very much for doing that. I'm still getting comments back from the meteorologists about that. They're very, very impressed with not only what they were able to see, they're impressed with the equipment, of course. You've got a giant Dobsonian or big old orange Celestron there. That's just an impressive thing to see. But they were very impressed with the club and the hospitality that was shown. And you might have noticed as you were working with people, there was a few more than just the meteorologists that were coming by. You had some random folks that were coming through for some concerts that were going on that evening. So got to do a little sidewalk astronomy, which is a very, very cool thing to do. So I like to throw this up. It really has only a few things to do with my talk, but this is the eyes on the Deep Space Network. It's kind of cut off on our screen here, but this is something that's available to you at home. You can look at it any time. This is live data, so we're looking at basically the same kind of screens that are shown in, well, JPL's version of mission control. So anything that is beyond the orbit of the geosynchronous satellites, for example, all that data is going to come through here. Whether it is an American satellite, American spacecraft, Japanese, European, this is the only capability that we as humans have to bring this kind of data down. So this is what we're looking at right now. And I highlighted Mars Odyssey, and we'll see a little bit of Mars Odyssey. This is the first time I've not seen New Horizons talking in a couple of weeks. We must be in a period of handoff between Goldstone, California, which is about halfway between Las Vegas and Los Angeles. Must be in a period of handoff as the Earth continues to rotate down to Canberra, Australia, down there on the bottom. But I just like throwing that up. So let's switch off to our...
What was the frequency of the downlink on Mars Odyssey?
That is, let me look on here. Down signal is 8.41 gigahertz, and up is 7.16 gigahertz. Yeah, the more interesting thing there is the power transmission. So the up signal, just on Odyssey, for example, is 18.29 kilowatts, and the down signal is 2.09 times 10 to the negative 21. It's just a little bitty signal coming back. We tend to build these giant, quite frankly, building-sized. It's a 70-meter 70-meter dish. It's really good at picking up what they call whispers from space. It's quite literally that faint. And as we get towards New Horizons, we're really going to get to understand a whisper from space. You guys good? I need to go on? Ah, turn the lights down. Awesome. So I wanted to share with you some information about planetary atmospheres, and this is something that I do with the broadcast meteorologist a lot. It's a great way to make a connection with meteorology, which is one of the few opportunities that the TV types have to really talk science on air. It's a good way to make those kind of connections to astronomy. And we're going to see as we go through this, there's a lot of connections that can be made to solar system formation as well. Before that, I'm going to throw up the slide, and some of you might have saw it earlier. Don't give the answers away. I'm going to throw up a slide that I have put up in front of the Elementary Educators Association, the North Carolina Science Educators Association, North Carolina Math Teachers Association, and most recently a room full of broadcast meteorologists. So let's see how you guys do. So just kind of look them over, come up with your answers in your head. This is actually the entire question here on the bottom. I know it's cut off a little bit, but that's the entire question. The very top one I put on there after the kerfuffle on the Daily Show, I think it was, with the way that the Earth was rotating in the opening graphics. When Neil deGrasse Tyson has been on, he's been on several times. The first time he was on, he pointed out that it was rotating the wrong way. And the second time he was on, he had a fit because they hadn't changed it yet. Yes? Have I? Okay, let me fix that real quick. Did not give away the answers? Or the answers there? I'll have to rejoin like this. All right. That's the right one. All right, that's the right. It's the right share. And there we go. Okay. So without further ado, looking down on Earth from the North Pole, you're looking downwards, counterclockwise or clockwise? All right, everybody got that one. All the broadcast vets got that one. All the science teachers got that. All the math teachers got that. The elementary school teachers, none of them got it. That is the reason we need to get out and do our outreach and particularly help the elementary school teachers. They get a limited amount of support and a limited amount of schooling when they're putting together their elementary education careers, so it's really up to us to help out there. So lunar cycle, so who can get the closest? Anybody want to shout one out? It's pretty close. Got to go down to the seconds, man. How about a tropical or a solar year? That's close. 365, 5 hours, 51 minutes, and 6 seconds. And this is cool when you're going in and talking to a little bit older age, when you can start talking about how this lines up with things like leap years. All starts to fall into place for people when they see these sorts of things. And then the lunar phases. AM, PM, all night, or you don't see it at all. Waning, waxing, full. How about waning? Waxing? Full. When you see them. So these are actually chopped off, so I'll just have to read it when I get my mouse back. So waxing's only seen in the evening time. Full is seen all night, that's correct. Waning's only seen in the morning. And when do you see a new moon? You don't. All right, so let's get started. So planetary atmospheres. I apologize for this being chopped off, but we'll deal here. Each planetary atmosphere, each atmosphere of a planet is going to have a couple different phases to it. An early phase is one that was created during the original creation of the planet, the original formation of the planet. And that's mostly coming from outgassing. So the kind of gases you're going to see there are very light ones. Gases that make up a planetary atmosphere are mostly going to come from accretion. They're going to come from outgassing of the planet itself. These early atmospheres, for the most part, were lost. And that's because during those early formation times, the planets were fairly hot, putting a lot of energy into the atmosphere, causing a lot of excitement, and enough excitement to reach escape velocity for these kind of gases. So that kind of kinetic energy is going to, of course, come from temperature. So we're going to see a lot of helium, we're going to see a lot of hydrogen. We're not going to see a lot of carbon dioxide at that time because that's a fairly low mass molecule, and it's not going to stick around in the atmosphere. So I'm going to keep going back to this graphic right here, and good, it fits. That's a good thing. So this was put together by a chemistry teacher in the UK. He's got a website, and let me see if I can get my mouse back and actually there. They tend to stick around in the atmosphere because of that. It's the lower mass ones that kicked out. I misspoke. So when you look through the different planets here, you start to notice some patterns. Notice the gas giants. They all tend to be made up of about the same stuff in about the same ratios. But when you look over here in the terrestrial planets, it's a bit more of a hodgepodge. So let's keep these in mind here. This high concentration of hydrogen, the high concentration of helium, as we look forward. So there's those gas giants. And as we go through these, it might come to mind, well, how do we know these things? How do we know what a particular atmosphere is made of if we haven't visited there? Now, as of New Horizons, we will have visited, at least as a flyby, every planet in the solar system, or former planet if we want to get very, very technical. But this is how it's done. So this is just basic spectroscopy, and we're able to, by the fingerprints that are provided by each one of these elements, able to tell what they are. And this goes back many, many years. I'm not an expert there, so I'm not going to dig into that. But what I want to point out here, so over on the left-hand side, that's the sun. Over on the right-hand side, that's Jupiter. So roughly 70% of the sun is hydrogen, and we're talking about the chromosphere. We're talking about the quote-unquote surface of the sun, what it's mostly made of. Lots of helium. Of course, it's a helium factory, and other gases make up just a little bit. But if you look over, this is Jupiter over on the right-hand side, we can see how close it is. So Jupiter's even been called a failed star. It's so very close to the sun, largely unchanged since its formation. Doing some reading on this as I was putting these slides together, I saw a couple of questions being asked about, well, could Jupiter become a sun? And the answer is, well, the chemistry is right there, but there's not enough mass. There's not enough mass there to actually kickstart that fission, to have it actually start producing more helium. It would take about roughly 25 of the existing Jupiters, and we all know how massive Jupiter is, for that to even be possible. So something that we notice and we can see with our own telescopes is that red spot. It's anticyclonic, which means it rotates counterclockwise, and that rotation takes about 6 days. Has anybody watched the red spot on Jupiter day to day to day? Done any observations of that? Yeah, it's something fun to do, and you'll start to notice those kind of rotations. We believe that red spot is roughly about 400 years old, or at least 400 years old, according to record. And something I didn't realize until I started looking up a couple of things on this, is that red spot actually extends about 5 kilometers above the cloud tops around it. So it is possible on some occasions to see some shadowing on the edges of the red spot. So moving on to Saturn, surface temp, and I put surface in parentheses here because, well, there is no physical surface. Now, perhaps there's a solid core, but the physical surface doesn't exist like it does on the terrestrial planets, but still, we're looking at between 200 below and about 176 above for that temperature. And I'm going to move through the gas giants and get on to the interesting ones here. Violent storms, of course. The winds have been measured at about 1,100 miles an hour near the equator. And ammonium hydrosulfide, not a chemist, so forgive my pronunciations. That's what's seen in those visible cloud tops there. And we think that there may be a liquid metallic hydrogen interior, or perhaps a rocky core. And the current estimates are that that core may be roughly 10 times Earth's mass. Now, what that volume is, don't know. I suspect it would be close to, or maybe a little bit bigger than Earth's volume, but that mass is definitely going to be much, much greater because of the incredible amount of mass in the planet itself. Anybody had a chance to see the rose? You probably won't be able to see it observationally from Earth, but this is an image from the Cassini mission. This is a false color. This is in near infrared. And this is one of the very first images that Cassini took when it was first launched. It's about 1,250 miles wide. So this is Titan. I wanted to throw one moon in there. It's about 1.45 atmospheres on the surface, so quite a bit of atmosphere there, quite a bit of pressure. 98% nitrogen. What does that remind you of? Anybody think of a planet that has a lot of nitrogen? Yeah, Earth. So this is one reason, one of many reasons, that Titan is so very exciting, and we're seeing a lot of talk about perhaps sending missions there in the future. Unfortunately, Europa has had its card pulled first, and our next big exploration point is going to be Europa. It's pretty exciting as well, but Titan would be pretty cool. So Titan does have seasons, so you can see the rotation of the planet here season to season. And you can also see that axial tilt, which I don't know what it is off the top of my head, but it looks like it's pretty close to Earth just staring at that. So, Uranus. We believe that it's still evolving from its original formation. And if you look at that makeup there with primarily hydrogen and helium again, it's made up very much like the sun. So that's an indication that it really hasn't evolved that much since it was formed. Has anybody had a chance to observe Uranus? Oh, almost everybody. Did it look blue to you? Yeah, well, that's coming from the capture of red light. That methane in the cloud tops is going to capture that very, very well. It is actually striped, and you probably didn't see that when you observed it. It takes a little more power to see that. This is a Hubble image. And it also will eat comets and other passing bodies, kind of the way that Saturn does sometimes, and especially Jupiter does. So what you're seeing over here on the right-hand side, those are our cloud tops following a comet strike. Then on to Neptune, 1,500-mile-an-hour winds, mostly methane. It actually has spots too. So every gas giant has some stripe patterns in them that we may or may not be able to see very well from Earth, but they're very similar in that regard. And then Pluto. We got to talk about Pluto. Pretty sure that its atmosphere is mostly nitrogen. Again, much like Earth, so that makes it pretty exciting. But what a lot of folks don't know is the atmosphere itself is about 350 times the volume of the planet itself. So its atmosphere extends way, way out. And the density close to the planet's surface is, of course, going to be much greater, but we don't know how much greater yet. If you go and look at the New Horizons website, if you go and study the New Horizons mission and the instruments that are on board, about 75% of those instruments and about 75% of the science that's going to be gained out of New Horizons is about that atmosphere right there. So atmospheric studies of these planets are really ramping up. So you can kind of compare where the top of the atmosphere occurs. Very, very thin out here, of course, but how thick it is close to the surface of the planet, well, we don't know yet. We're going to find out. So let's get started with the terrestrial planets. Mercury. We're pretty sure that what little atmosphere is there is still coming from outgassing. Atmospheres tend to come from outgassing of the planets themselves. But some of the particles, some of the molecules in the atmosphere may actually be coming from the solar wind, may be deposited by the solar wind, only to be stripped away very shortly after. The solar wind is what is taking Mercury's atmosphere away. Surface temperatures vary 280 below to 800 above, and I forget the rotational period on the planet itself, but it's very many months long, so it's a very, very slow rotating planet. So it's going to be sitting in direct sunlight for a good long time, and the backside of the planet is sitting in complete darkness a good long time. So 1 trillion times thinner than Earth, very, very little atmosphere. Not to the proportion that New Horizons had, but the recent mission to Mercury that was run by the Applied Physics Laboratory up in Baltimore did do some atmospheric studies. When they ended that spacecraft's mission, normally when you want to destroy a spacecraft, you simply take it to the atmosphere of a planet, and more often than not, and we'll see as we get to the other terrestrial planets, the atmosphere is thick enough to not only slow the spacecraft down and deorbit it, but it's also thick enough to actually burn it up in the atmosphere. Not Mercury. When it was deorbited, that was a very slow process. The final destruction of the spacecraft did not happen in the atmosphere. They called it geobraking. They actually slammed it into the surface of the planet, and the atmosphere didn't provide much help at all there. So there's an atmosphere on the moon as well, as you may know, and Mercury's is even an order of magnitude thinner. Another reason that Mercury may have lost most of its atmosphere is because it lacks the gravity to hang on to it. It's mostly that solar wind whipping at it at all times. So let's look at Venus. Roughly 90 atmospheres. And does everybody know what an ATM, what an atmosphere is? It's one is comparable to Earth. So 1 ATM is comparable to kind of a normal pressure here at sea level on Earth. So Venus, very thick atmosphere, lots of CO2, a little bit of nitrogen, a little bit of other gases, but there's clouds of sulfuric acid that are floating around. The source, again, we believe to be to some point outgassing of the planet itself, but also volcanic activity. That's where that CO2 is going to be coming from. There may be a little bit left over from when it was originally a planet. We've sent one mission there. Actually, the Russians have sent one mission there. Got some very brief pictures back, but we did learn this kind of information about the evolution of the planet. So over on the left-hand side, that's going to be closer to the equator, where you see this kind of cartoony-looking volcano. As you get closer to the poles, that's where you see polar vortexes, the same kind of atmospheric pattern that we see here on Earth. It's going to be a rotation pattern, happens up around the poles. It's going to continue mixing that atmosphere. The temperature does get colder as you go up to the top of the planet, just like it would here. And we're seeing layers of clouds and different atmospheres. Very, very thick. It's going to retain the heat very well. The astronomer who originally came up with the idea that Venus had a runaway greenhouse effect, his birthday was yesterday, I believe. It's back in I want to say the 30s that he came up with that idea. So here's a different view of it from the side. We're seeing a constant rotation of the atmosphere from the poles down to the equator, very much an opposite, 90 degrees twisted from how we would see it on Earth. We do see signs of volcanism. Much of the gases that we see in the atmosphere are going to be coming from volcanism. So here's an interesting comparison of pressures between Earth and Venus. So you got pressures on the y-axis. The x-axis has temperature. Earth, we have a different type of layering in our atmosphere, and it causes different temperature gradients. It's very much smoother with Venus. There's not that much variation in the atmosphere. It tends to be a bit more pure. We don't have the layering like we have in Earth. So here's Earth, So where did our atmosphere come from? Of course, outgassing was quite a bit of it, but this great amount of nitrogen, where did that come from? One of the prevailing ideas is that this came from perhaps a visiting comet. During the time after that initial atmosphere was stripped away either by solar winds or heat activity in the planet itself, causing those atoms to be excited enough to reach escape velocity. Where did that nitrogen come from? So abundant nitrogen. Nitrogen also doesn't react very well with solid Earth, so it tends to be something that the gravity can hang on to as well. It's also very stable in the presence of solar radiation, so it doesn't get excited enough to reach those escape velocities. So we also see quite a bit of these kind of chemicals in our atmosphere that are unique to Earth and then maybe Venus. So those are going to come from volcanic activity. So I should leave the moon in here too. We should definitely think about the moon. Not a planet certainly, but we have done quite a bit of studies on lunar atmospheres, surface temperature again, 387 below to 253 below. Actually, that should, yeah, that's positive, to 253 above. Again, the same kind of issue as we have on Mercury. Without a protective atmosphere, the temperatures tend to swing very, very widely. So that's a not dark side of the moon, but that's a shadowed side of the moon. So whenever we were planning the Apollo missions, the initial ones were planned during full moons. And the reason for that was to avoid the danger of landing in a shadowed part of the moon. All the planning had been done for full daylight, both so the astronauts could work easily and also to avoid this temperature problem here. The suits had not been engineered to deal with that. Yes?
On the second line up there, it says surface temperature minus 387 Fahrenheit.
Mm-hmm. The latter is a positive.
That's supposed to be a positive.
That is a positive. Mm-hmm. So the other reason that it's hung on to what little atmosphere it has is that the gas molecules are actually so widely spread that they rarely even run into each other. So they're not going to get that kinetic energy from there. The only energy they're going to get is from the sun. That's how thin that atmosphere is. But all in all, we really know not a whole lot about the lunar atmosphere. But we have discovered that even the surface experiments that were left on the surface of the moon by the Apollo program is outgassing. The bit of study that has been done, we've actually seen a higher atmospheric concentration around these experiments. It's that thin that we're able to impact it simply by bringing something up there with us. So this little factoid I found while I was doing a little research that I like to keep in my back pocket. The total weight of the atmosphere on the moon is the same as a loaded dump truck here on Earth. So now to the fun one, now to Mars. So again, lots of CO2, very different from a gas giant, also very different from Earth. Surface temperature, it's going to run between negative 200 and about 80 Fahrenheit. Again, that's positive as well. And we have, this is the only other place in the solar system where we have a daily, actually hourly reporting weather station. And I'll show you her in a little bit. So approximately 1% of the atmosphere of Earth. And it has seasons. It also has an axial tilt, 23.5, pretty close to Earth's. Seasons work quite a bit different on Mars, though. And the reason for that is the quite a bit more elongated orbit. So this is a depiction of that here. And these numbers, the LS numbers, are in degrees. It runs from 0 to 360, of course. We just recently ran past the autumn equinox. So we're into, I'm sorry, did we run into the spring? I'd have to look that up. But we just recently changed seasons here. And the temperature differential is quite a bit different from season to season. It's because of this elongated orbit. Yes, please.
So you have right there the seasons made out of this business
Mhm.
here. So you have autumn, winter, spring, summer. Now, are you saying that that applies to the planet? Oh, wait a minute. Yeah, I did this. It's northern hemisphere season. Okay,
Yes,
never mind.
it works the same way Earth does. Again, because we've got the similar tilt. When it's winter in the north, it's summer in the south, and vice versa. The extremes tend to be a little bit different because of that elongated orbit, though. When we look at the temperatures coming off of the Mars rover, they tend not to vary that much, and it's because it was landed about 5 degrees south of the equator. We haven't gotten good at landing rovers in the north or south pole regions. We could put landers there, no problem, but the rovers, they tend to like to put in a little bit safer areas closer to the middle of the planet.
So sometimes at the apiary, the pole can be pointed toward the sun and sometimes away.
Right.
Okay, so there really is a lot of difference.
There's quite a bit of variation there, yeah. So when somebody asked the question, well, what season is it in at Mars? We can look at the LS number, and that kind of gives us a clue. But to your point, the variations depending on where it is and where the sun is does make quite a bit of difference. So I just have to put this slide up. If you've heard me speak elsewhere, you've probably seen this slide before. And the rest of the family is cut off here, but so Spirit is no longer operating. She's over on the left-hand side. She's stopped at 2208 sols, and a sol is a Martian day. It's about 34 minutes longer than a Earth day. So she reached 2,500% of her mission. She clocked out at almost 5 miles. Opportunity is still operating. She's getting on in age, and when we all get on in age, certain things stop working as well as they used to. She's got a bit of arthritis in her robotic arm. They figured out some ways to get around that and keep her running. She's got a bit of a memory problem. As we get on, I think we can all appreciate that as well. She's got 4 banks of memory, and luckily it was the last bank. It's accessed serially. So luckily it was the last bank that went bad. If it was the first bank that went bad, we wouldn't have a mission anymore, but it's the last bank. So we just have to be a little more judicious in what we store there. But she continues on. So she's at Sol 4058. It's cut off on here, which is 4,500% of her mission. And she recently passed 26 miles. So they had a big celebration back at JPL for her reaching marathon distance. I think it's kind of cool. Curiosity just passed today is Sol 1026. We're at 150% of its primary mission, and she's a little over 6 miles. So I want to share some of the weather patterns, some of the atmospheric conditions that we see on Mars. They're very similar to what we see here on Earth. These are actually water ice clouds that were recorded by this is recorded by Opportunity back in 2006. So this is a series of images that have been placed together to create the animation, but it looks like what I saw going over my office this afternoon. And this was in a winter period. Happened to be October here on Earth, 2006, but it was winter on Mars. So we see storms on Mars as well. This is an animation that was created from the Mars Odyssey orbiter, and it passes over the planet in stripes. That's why you see that kind of stripy pattern on the globe that's spinning there. But it's constantly monitoring the cloud formations and also the dust patterns that can happen throughout the Martian year. Periodically, we'll see planet-wide phenomenon, something that we don't see here on Earth, something that's happening all the time on Venus, but on Mars it's a less frequent pattern. We'll see planet-wide dust storms that will completely block out the planet. You cannot see any of the remnant volcanoes. You can't see, even the polar ice caps will be blocked out by these storms. So with this particular report that came out from MRO, and these come out weekly, there's a organization down in San Diego that reads this data in and puts out weekly reports, puts out these animations. So it's kind of like your normal weather report that you turn on TV and see, but it's coming from Mars. This particular week, there was a dust lifting event near the southern area there. Water ice clouds, we always see water ice clouds in these reports. Those tend to form kind of in the equatorial regions. Occasionally we'll see them up closer to the edges of the poles. We see a couple of local storms. And the Mariner Valley, we'll see storms kicking in and out of that valley as well. Yes?
Like small white circles. See when that thing was rotating.
Let's see if we can make it happen again.
Like that one right there.
This one right here?
Yeah.
That is marking the location of a rover. So judging by where that was, that looks like that's probably Opportunity. And that looks like that's Curiosity. Good catch. And you can see some pretty thick clouds that are coming up in the rotation here. Yes, that's correct. I'm glad you asked it that way. Often when I show this to the general public, the question is, what don't you want me to see there? Nothing. We want to see that too. Yes. So here's a view of the Gale Crater where Curiosity is currently landed. And something really cool happens here atmospherically every day, and we can measure it with the instruments on board Curiosity, and it is just as regular as the sun coming up and sun coming down. It is a heating and cooling effect that happens on the floor of the crater itself and the mountain that's rising up out of the middle of the crater. So as the sun comes up, it heats one side, causes all of the air there to heat up as well, the atmosphere to heat up as well, and causes a movement because of that increased pressure to rise. It creates a rotational effect within the crater. That air will move around the crater, it will move up and out. We'll actually see a bulging planet-wide. So what you're seeing here is a look down from the top of, from the North Pole. That's the rotation that's occurring, just natural rotation of the planet. As that side of the planet heats up and heats up the atmosphere, it extends out several miles, causes it to bulge out. This leaves a vacuum, if you will, down at the down at ground level, and air will rush in from around the cool side of the planet, the night side of the planet. The planet just continually rotates under this. It's a really neat effect, and I'll have a image in a section that shows evidence of that from the rovers. But this is evidence of the dust. So this is something we don't deal with around here, but if you were forecasting weather in a desert area, you'd be thinking about things like dust. So this is an instrument that's used to measure UV light. I believe this is a Russian instrument, but they had a pretty good idea of how they could protect the instrument itself. So anybody guess what's causing those rings around there? Anybody guess what they might have put on board to? You're close. They're rare earth magnets. So there's a series of rare earth magnets are mounted beneath this faceplate, and it creates a magnetic field that when a random piece of dust comes along, it deflects the dust. It's just enough to change the trajectory, and it keeps it from hitting that sensor. It's done a really good job of keeping those sensors remarkably clean. So the goal here isn't to gather the dust, that just kind of is a byproduct. The goal is to create that field to cause that deflection to happen. But being up on Mars, we don't have an opportunity to go up there and clean this thing. So this has worked pretty well. So going back to Sol 36, again, the 36th day after landing, see how clean it was, and up to 881. I've not seen an image taken of this recently. I probably need to update this as soon as that comes down, but you can see what kind of filth that we've got built up over there.
I think one of the rovers have what do you call those cyclones on Mars?
I think I've got a slide on it in a moment. Dust devils. Yeah, absolutely. Dust devils have been imaged by the Spirit and Opportunity rovers, the little golf cart-sized ones, and they absolutely have contributed in cleaning of the rover's solar panels. Not as big of a deal for Curiosity. Curiosity is nuclear powered. It's powered by a nuclear power source. We don't have to use the solar panels. But there was a significant degradation of the power that was being supplied to these rovers by that dust. And this kind of evidence in here, how much it can build up. And simply having a dust devil appear close enough was enough to blow it off. Now, we've not recorded any dust devils so far with Curiosity. We've not imaged them. So they've not occurred in front of the rover or behind the rover in view of the navigational cameras. However, we have seen evidence of them. And the evidence suggests that the dust devil went directly over the rover, out of view of the cameras. Can anybody guess what that evidence might be? That might work, and how that worked in this case.
Were they measuring pressure?
Pressure, exactly. Saw a significant dip in pressure that lasted a few seconds, and then went right back up again. What else could it be? Saw some cleaning on the rover as well, so it's a pretty good indication that it was a dust devil. Yes, sir.
On that picture right there,
Uh-huh.
device, I wonder why they didn't use Phillips head screws to attach that plate instead of just those.
If you want to understand NASA fastener rules, I've got a document for you. It's a really good read, especially if you're having trouble going to sleep at night. There is a document that is specific about why they use what they use. There is another one that is even more fun of a read, and it's about knot tying. How they tie off all these different cables. You can see some right there. Oh, yeah, that looks like an engineer screwed up, doesn't it? Yeah, I don't know the answer to that one.
With slotted head screws, you have a problem with the screwdriver jumping off the screw.
Well, we're not putting a screwdriver on this one very often. Yeah, once we got her all buttoned up in the clean room and up on top of her rocket, she's on her own. You will notice they've got Loctite all around it though, so that very well may be some silicone as well. Yeah, there's a fair amount of Loctite used in the aerospace industry too.
Of course, just so they're stainless steel, so they won't rust.
Very possibly, but not a whole lot of moisture up in the air there. We do see humidity in the air, but not enough to probably create much rust. So these are the two instruments that are contributing most to our knowledge about the atmosphere on Mars. They're a little bit bigger than a good-sized cigar. It's called the REM system, Rover Environmental Monitoring System. This is the one instrument that was damaged during landing. The only one. We're getting some good data from the REM system on things like temperature, on things like air pressure. But unfortunately, the wind sensors were damaged. And that happened during the entry, descent, and landing phase. If you're familiar with that, you know that it was lowered down on a series of cables and was being dangling from the top of what kind of looked like a backpack for the rover with retro rockets on it. That was enough to stir up dust. We could actually see on the surface of the planet where that dust was stirred up from orbit. It was significant enough. That dust was enough to kick up into these instruments and damage them. Fortunately, the 2020 rover, which is going up in 2020, the spacecraft bus, the wheels, the power system, the actual rover body, pretty much the same as Curiosity. Quite a bit different instruments going on board that one. Obviously, we want to put some different instruments up there. Just about identical rims. So we're hoping that the wind sensors survive that one, and we can get some good wind data. They did some neat testing of these instruments here in a wind tunnel. Just by the orientation of these two instruments, they're extruding out from the main mast here. The way that they're configured, we should be able to get wind measurements 360 degrees around. That is, if the instruments worked. So I always have to throw this up. I got to pimp my Twitter account. So this is Mars Weather Report. It is monitoring the data coming down from Curiosity. And about every other day, on average, we're able to get a report out of it. The RIMS instrument is actually gathering data every 5 minutes. It is autonomous enough that if there's some sort of a weather event that's occurring, if there's some drastic change in pressure or temperature or something like that, that it can start gathering data at a much greater rate. But this kind of information, summary information, comes down about every other day. This is one of the first tweets that we've gotten back from the Curiosity rover in a couple of weeks. And the reason for that is we haven't seen Mars for about a month. It's been behind the sun. You may have noticed if you've been out there doing your observation. It wasn't physically behind the sun. It didn't actually pass behind the disk of the sun. But it was close enough to that corona. It was close enough to all those charged particles that are mixing around out there in the chronosphere that we didn't want to run the risk of sending commands to the rover that could be garbled. We also didn't want to run the risk of it trying to send information back because the way the daily operations of the rover go, it's going to have some body of information it needs to send back. It needs to get an acknowledgement that we received them, or it will continue resending them. And it sends it back through a combination of when the rover has a direct line of sight back to Earth, it will directly transmit things back. But more often than not, it's going to uplink them to one of the passing orbiters, Mars Odyssey, the Mars Reconnaissance Orbiter, that's going to use a store and forward type of mechanism. And that's very useful when the rover's on the opposite side of the planet than Earth, so we can still keep a good communication line open. So this is the most recent one. So Sol 1021, June 21st is what the equivalent is. This data comes down, but it could be a constant in the little Python program that's doing this, because it's always sunny. We haven't seen any clouds over the middle part of the planet in a couple of years that are enough to say that it isn't sunny. A high of negative 15 Celsius, 5 Fahrenheit, so fairly warm. It can get up to 80 degrees. I have not seen it up to 80 degrees in a long time. The low is generally down around negative 100. So there's the pressure, 8.48 hectopascals. Anybody familiar with that scale? It's around 1,000 would be closer to what Earth would be. Yeah, it's millibars, exactly.
Tony, presently there's no way for them to measure surface radiation?
There is. I don't include it in here. It's not something that's generally very understood by the public, but surface radiation is absolutely being studied by an instrument called RAD, Radiation Detector. It's a Russian instrument, but very valuable information that's being stored and studied very closely. If we ever want to send anybody to Mars, we want to send people to Mars, we really have to understand that. We're most likely going to send somebody to this kind of equatorial region anyway, so it's a great place to gather that kind of information. That's a good question. So if you want to get bugged on your cell phone by Mars weather, you can follow this one. So here's a little bit more on the capabilities of this weather station. Boom 1 and Boom 2 are identical, so the fact that it's cut off here is not a huge deal. Wind sensor, wind sensor, wind sensor, those are all offline. Air temperature sensor is working great. Humidity, I don't have any slides on that, but we do see humidity changes day to day to day, and there is a bit of water vapor in the atmosphere. To the point there, that is a consideration for a possible water source on Mars. It's so very thin, though, it probably wouldn't make a very good water source. You'd be better off digging into the ground and pulling water ice out from beneath, which we've found at this location as well. So here's the graph that I was referring to earlier. You can see we've got the small version of it up here. So this is the evidence of that bulging effect of the atmosphere on the sunlit side of the planet. So this is over the major tick marks here. Every other one is a sol. That's half a sol. So this is a Martian day. This is a Martian day. This is a Martian day. So you can see where day and night occurs. And the absolute regularity of it is the really interesting thing to me. This kind of pattern here, this shape to the graph, probably wouldn't be there if it wasn't for the location where the rover is. This is a bit of impact from the canyon walls, the crater walls, and that air rushing in and rushing out causes this to delay a little bit. If it were on flat air, this would probably be a lot smoother of a, or on flat ground, this would be a lot smoother of a graph. So going back a ways, here's Phoenix, and also doing this same kind of measurement at the poles as opposed to the equator where Curiosity is. Lots and lots and lots of measurements, but the thing to look at here, so 0 to 180, this is a year. This is the change of seasons. So what you're looking at here is water vapor abundance, but against vapor pressure. This same kind of shape, if we were to look at just pure atmospheric pressure, would look the same way. And the reason for that is, has anybody looked at Mars observationally over, say, a 2-year time frame? Have you looked at the poles? Have you looked at the polar ice caps? What has happened to them over that 2 Earth year time frame? They've shrank and they grow. Where's it going? It evaporates. That's carbon dioxide ice. That's dry ice. And as more energy goes into the atmosphere, as it gets into a summer time frame up in the northern atmosphere, or northern hemisphere, that energy goes into the poles as well, and that dry ice sublimates out into carbon dioxide gas. That's exactly what's happening here. There's more atmosphere, therefore more atmospheric pressure. And with the instruments, with the missions that have been up there for a couple years' time, we see a consistent pattern here, with the pressure growing during the summer as that carbon dioxide ice gets converted back into carbon dioxide gas.
So it shrinks like that. So under the dry ice, is there water basically? So what I'm getting at is that when most of it is significantly sublimated, is that what we're seeing now, mostly ice, water ice?
Water ice is a component.
An actual, like Antarctica.
Right, right.
It's like multi-year ice that never actually defrosts.
Right. The same kind of a concept. There is a mixture of carbon dioxide ice and water ice up there. So it goes in and out of the atmosphere the same way. What we are looking at when we see the polar ice caps during the Martian winter is carbon dioxide. Yeah. And it will snow. It's very small crystals as it's being cooled out of the atmosphere and returned back into a solid form during the winter.
A similar graph with carbon dioxide, it might lead this graph in terms of speed.
Very likely, yeah, very likely so.
Wouldn't that actually create the possibility that actually purifies the water ice because the CO2 is boiled out of it and then redeposits in this fluctuation?
Yeah, they tend to be a little bit separate. The water ice tends to be deeper. It tends to be, and we saw that with the Phoenix mission too. There was a scoop on the end of a robotic arm that the very first time they put that into the soil, drew it back, first thing they saw was water ice. And the water ice sublimates in a lot the same way that the carbon dioxide ice does as well. It goes straight to a gas, which is why you see it in the atmosphere like this. So here's another view of that. Shouldn't call it cyclonic action because that implies more energy than is actually there. But we do see a rotational action around that, around Mount Sharp in the middle. So this is the location of the rover. We'll see it rising up the mountain and also exiting out of the crater itself. So the plan with Curiosity, she's about right there now, but she's going to continue driving up this mountain as long as Congress continues to fund her. Yes, sir.
What the hell high that mountain is roughly?
Ian, do you know that off the top of your head?
When you say the valley, it's a couple of miles.
Yeah. It's not Everest high.
No, it's like 3.5 or 6.
What's the tallest mountain in North Carolina?
Mitchell.
Is it Mitchell High?
Yeah. 6,684.
Okay, it's not even Mitchell High then. So this crater here was formed by wind. It wasn't actually formed by an impact. and it also was full of water way back when. So that's why we're finding so many things there geologically.
Now, Tony, I know that they can't measure wind speed, but if they're able to collect data fast enough and they see pressure differences, can they not back calculate based on the variations in pressure to get an idea, a ballpark idea, what kind of velocity?
That is precisely how this information there was gained. Yeah, we're able to make some assertions about direction and speed. Not as good as if we had those instruments working, but yeah, that's precisely where this information came from.
Tony, is there any place on Earth where that phenomenon occurs like that?
I don't know. That's a good question.
5.5 kilometers.
Thank you. 5.5 kilometers.
It would be interesting to see at such a place.
It would be, especially on Earth, where we would be able to sense this a whole lot better than we would on the thin atmosphere of Mars. But physics works on Earth the same way it works on Mars, so there's got to be somewhere like this. So here's another view of that ebb and flow of carbon dioxide in the atmosphere. So this is summer. Yeah, isn't that cool? It's the air currents. That's from the dunes that are created up there. Very similar to the dunes you would see out on the coast. There are folks at JPL that do nothing but study those sand dunes. They're interesting people to talk to as well. And as these spacecraft pass overhead, just in the past year or two, they've noticed this carbon dioxide. As it builds up over time, it'll pack down and become far more solid. If it happens to be on the top of one of those dunes and gets solid enough that gravity can take over, you'll see that thing go skittering down the side of the dune. Yeah, so do a Google lookup on carbon dioxide slide or something like that, and you'll see paths that are left by these blocks of carbon dioxide that have built up over time. Not en route.
Yeah, the same thing that happens in Death Valley. Rocks. And nobody could figure out how the rocks were moving, and they realized it was frost. And the rock would get on top of the frost from the cold night, and the wind would blow it across.
That and the frost itself had some leverage to it that would create some motion there. Yeah. So that's summer, and there's winter, so you can see the difference between the two. This has got to go somewhere, and it goes up into the atmosphere. So this is actually from RIM. So this is shortly after the rover landed, from Sol 20 up to Sol 200, and you can see a pretty consistent growth of air pressure there, as that turns into that.
Now, what's going to happen when it goes back to that? Is it going to be able to drive through?
Well, this is all happening up in the poles.
I thought.
Yeah, we're not seeing any carbon dioxide snow at the equator where Curiosity is. So that's all happening up in the poles. Not really, not really. But the cool thing is that this is all happening up at the poles and is very, very measurable as a part of the overall atmosphere down at the equator. Oh, good, I do have this slide in here. Couldn't remember if I put this one in or not. So here's your dust devil. Those are real images. This isn't an animation. Well, it's an animation of several photos put together. This is an animation, but it's based on data from the Mars Reconnaissance Orbiter. This will loop through again, hopefully. I'll make it loop through again. There we go. Now, one of the theories on why we haven't seen a dust devil that well defined over Curiosity is because it's down lower. It's down in a crater. So these kind of dust devils will move along for miles at a time across more flat plains. Opportunity and Spirit are more in flatter areas of the...
Did they relate it to a specific pressure threshold?
As to what kind of conditions would... Yeah, before we can start looking for them and start expecting them. I don't know the answer to that. I don't think we have a Fujita scale for Mars. And keep in mind, too, the reason we can see that is because of dust lifting. It's simply pulling dust. We see the same thing here on Earth. I've seen videos on YouTube endlessly in parking lots of these kind of things happening.
Well, but now the Earth dust devils are heat driven. These aren't heat driven. They are heat driven. Okay.
It's heat exchange. They're formed the same way we here on Earth. Yeah. So here is again that REMS pressure instrument, and this is the evidence that we have that dust devils have occurred over the Curiosity rover. Simply the pressure differential is the only thing we have there. So the scale down on the bottom, and I apologize for not being there. So this is 0. That's about 10. That's about 15. And all the way over here is about 20, and that's in solar hours. So that's Mars hours. So you can see that it was we can see the dust devil approaching, and the actual event where it went over happened over just probably 15, 20 minutes. So these are temperature differentials. This is air. This is ground. So there are a pair of temperature sensors on board, both air and ground. And one of the engineers out at JPL described it to me this way, and I don't know of a better way to say it. It can be summer at your feet and winter at your head. That's how differential it is. And you can also see that the max and min down on the ground level is quite a bit different, which I find very interesting, but I guess it's a matter of how much heat can be retained in the geology, which is also not my specialty.
The amount of water vapor on Earth have a lot to do with smooth out our pressure. Our temperature.
It does, and the amount of atmosphere that we have smooths that out quite a bit, and quite frankly, the clouds do too. So you notice how this morning we had a pretty consistent low 70s, mid 70s, but as soon as those clouds left, it got up to 90 again and ramped up pretty quickly. So that's a bit of a greenhouse. It keeps the temperature very constant. So I got to throw my shameless plug up as well. So again, Mars weather is something to follow if you're interested in these sorts of things. I wrote an article on these instruments and what their capabilities were and what we were hoping to learn from them in a magazine called Weatherwise, which is part of the AMS offerings. And of course, I rant about this stuff on WRAL quite a bit. So something about WRAL I got to share with you guys too. Go online tonight and take a look at their live streaming camera. You think it's bad watching paint dry or watching grass grow? They've got a live streaming camera watching ice melt.
Yeah.
Okay, so they put out this morning. They had a local ice sculptor. You might have seen their ice desk from back over the winter. So this same sculptor put together a sculpture with the logo, stuck that on top, and then put out 6 300-pound blocks of ice. Put it out in a baby pool, and it's bragging rights. When's it going to melt? So I started doing the math on it and got bored with it really, really quickly, because it was a lot of differential equations that I was not really interested in messing with this morning. But I went ahead and called my shot and said 6 a.m. tomorrow. Several of the meteorologists there are saying 2 or 3 o'clock tomorrow afternoon. The fact of the matter is there's so many variables, who knows?
Somebody actually, and I saw it this morning, I think it was somewhere between the 8:30 and 9 o'clock session. Somebody actually warned them not to waste the water.
Well, they specifically put it in the baby pool, so that they could capture it, and they're going to carry and put it on the plants. It's sitting on some foam core, so that was originally put there because at some point this is going to fracture. It's probably going to pop that pool because it's an inflatable kiddie pool. But it actually provides a bit of insulation too, so the heat coming up from the earth below is not going to melt it. But yeah, go take a look at that. It's kind of fun, and throw in your guess on what it's going to be. So I wrote something on the blog this morning about what my guess is and why it's going to be wrong. And the answer is there's just too damn many variables. We just don't know. So with that, I've got time for questions about this atmospheric stuff or anything else.
Does magnetic fields or the lack of magnetic fields have any effect on the atmosphere?
Absolutely. So we have a wonderful magnetic field around Earth that is